Welcome to a lesson with Dr. Powell. Let's take a look at how we can find the instantaneous rate of change of this function right here, square root of quantity x minus 2, at an arbitrary point x. So what's the slope of, so here's the curve, right? So basically, if I give you an x value, I want to know what is the slope of the tangent line right there. What's the slope right there? The slope at x. The nice thing about this is going to depend on x. It's going to be a formula or an expression in terms of x. So we're going to get a formula such that when we, okay, so for this function right here, let's say I want to know what the slope of the tangent line to this curve is at maybe like 5. Then what would I do? I would say put x equals 5 into this formula and get out what the slope is. So I'm getting a formula for the slope of the tangent line at any point x on this. That itself is it's an expression in terms of x, and we can set a function equal to it. That's going to be called the derivative function for this function. All right, so that's what we're going to do, and we're going to do this using a limit. All right, so let's go for it. So to do this, we are going to set up a difference quotient limit. We're going to use what I've been calling the A strategy here in the different videos that I have. So we're going to pick 2 points. One point is simply going to be, wait a minute, where we want to find the slope of the tangent line at x, right? Slope of the tangent line at x. So this is x. What is the y value? We'll put x into the formula, and you get at square root of x minus 2. Now let's plug in a point nearby. Okay, and really what we're going to be computing in this fraction is the slope of the tangent line here between 2 points. Of course, as these points get closer and closer together, the slope will limit toward the slope of the tangent line. So we pick a point nearby. Instead of it being at x, we let it be the x value just simply be a. All right, then plug a into the formula, a minus 2. So we're going to get 2 points, x comma square root of x minus 2, and a comma square root of a minus 2. We find the rise over the run. Okay, so subtract those 2 y values divided by those 2 y values, a minus 2 minus square root of x minus 2 all over a minus x down this way. And we're taking a limit as what happens as this value of a gets close to x. Limit as a approaches x. Notice that in this, so one of our points is just, so this point right here that has x in it, that's going to be the point we're finding the slope of the tangent line at, and a is heading toward x. All right, so now in here, realize that we see a's and x's in this limit expression. But really, what's the variable that we're concerned with when we're taking a limit? It's a. A is what's changing. A is what's getting close to something. X is behaving like a constant. So in this limit, x is a constant. A is the variable, but x is just some kind of constant. A is heading toward that point, x. Okay, so this is really a function of a, and we're thinking, okay, so we can't just plug in a is equal to x, which is what this is saying, because we have a domain problem. So we look for an equivalent fraction algebraically, where the domain actually has x in it. A can be equal to x then. So we go ahead and we proceed that way. So let me just go like this, and let's multiply top and bottom by something that'll help us. Now notice that the numerator looks fairly complicated, but the domain problem is in the denominator. But if we can somehow change the form of this so it has like an a minus x factorable out of it, then you could cancel things, and the domain would change, and you could plug in a equals x. So what we can think of is difference of two squares, right? Because we would rather, instead of the square root, we'd rather have it squared to just be a minus 2. So in order to do that, we think to have a minus, and then here we can have a plus. And the benefit is when we think of difference of two squares, a minus and a plus, the same two things right here and here, then what we get is the first thing squared minus the second thing squared. The middle and outside parts of the FOIL will go away. We have to multiply the top and bottom by the exact same thing. And so same thing right here. And notice on the top we end up getting limit as a approaches x of a minus 2 minus x minus 2, and that is going to be all over a minus x square root of a minus 2 plus square root of x minus 2. Okay, so on the top right here, notice that this when we distribute this negative here, negative here, so this is really going to become a positive 2. That negative 2 will cancel, so that'll be nice. And then we'll be left with this a minus x. Wait a minute, so the whole top is a minus x times 1. It's a minus x is a factor of the top. Note, and it's a factor of the bottom, so we can divide top and bottom by quantity a minus x, which is the same as canceling. And what are we left with? Just 1 over this. Now in taking a limit, now it looks like we can plug in x for a and things will be okay. So so this a, we can replace it with x, and we have a 1 on the top. So then we have square root of x minus 2 plus square root of quantity x minus 2, which is equal to 1 over 2 square root of x minus 2. We just found the instantaneous rate of change by taking a rise over run of an average rate of change and taking a limit, and we found it. And it was, the nice thing about it is it's at a point x. This right here is, we have a function. This function is called the derivative function of this one. We call it it's derived or comes from this one right here. We say f prime of x is equal to what we just obtained, and kind of nice. So for instance, let's say we want to find the slope of this curve, the tangent line, the slope of the tangent line of this curve at x equals 6. So we could say f prime of 6. What would that be? So we can plug 6 into this formula. You notice you have 1, 2, square root of 6 minus 2 square root of 4. Hey, that's going to be 1/4. Because square root of 4 is 2. 2 times 2 is 4. So slope is going to be 1/4 when we're at 6. Thanks for watching.